Now we talk a little bit about the projection. So we've got a vector v, a vector w, just a typical picture of some vector v and some vector w. The projection of v on w, the scalar projection, is this side of the right triangle you get when you project the v vector onto the w vector. You go to the tip of, you put the initial points of the two vectors together. You go from the tip of the v vector projecting at a right angle down to the w vector, and what you get here is called the projection. That's the scalar projection. This PROG is just the number that indicates the displacement from here to here. Could be positive, could be negative. If theta is greater than 90 degrees, your projection would be in the direction opposite w, which would make it negative. Scalar projection. Okay? Now, the scalar projection, if you look at this triangle, is clearly just the magnitude of v, which is the length of this vector, times the cosine of theta. So, in this right triangle, this side here is this side times the cosine of this angle. So that the projection is magnitude of v multiplied by the cosine of theta. Now, if you're conversant with dot products, you would probably see, or you might well see, that that is part of the definition of the dot product of v and w. The dot product of v and w is magnitude of v times magnitude of w times the cosine of theta, where theta is this angle. If we divide this expression by the magnitude of w, we get magnitude of v times cosine theta. Now, if we write it this way, of course, we could write the numerator here as v dot w, and the denominator, of course, is a magnitude of w, so that the scalar projection, the signed length of this side, again, the length of this side positive in the direction of w, negative if in the direction opposite w, is just calculated from v dot w over magnitude of v. And that's not a formula to be memorized, although it doesn't hurt to memorize things. That's something that should, every time you see it or think about it, should come out of this picture, because the connection to this picture is so obvious. If you just remember it as a formula and don't have the picture, you lose the meaning of the formula, you lose the meaning of the calculation, and you don't retain it. You will retain this picture and what you do with it in order to get this. Okay, now we also have the vector projection, which is this purple vector from here to here. Okay, the scalar projection is just this distance, but positive if in the direction of w, negative if in the opposite direction. The vector projection is a vector in the direction of w with this scalar multiple. Okay, and we get that very simply by multiplying this scalar by a unit vector in the direction of w. Okay, so if the projection is the length of this side, we multiply the length of this side by a unit vector in the direction of w, and we get a vector in the direction of w whose magnitude is the length of this side. If the scalar projection happens to be negative, of course, that's going to give us a vector back in the other direction. Now, how do we do that? Again, we just multiply this, magnitude of v cosine theta, which is just this, multiply that by a unit vector in the direction of w, and we know that to get a unit vector in the direction of w, we divide w by its magnitude. So what we're doing is we're multiplying the scalar projection, which could be positive or negative, by a unit vector in the direction of w to get this vector here. Okay, very important idea, and pretty easy to see in terms of the picture. You should work on this until you really have that picture, because this is something that will come up again and again, and the better you understand it now, the less confused you'll be later when we apply this in situations that have some complexity.